Hello, welcome back. Right now, we are going to be talking about continuity. Continuity. All right, so continuity comes from a concept that you should have already heard of at some point, which is the idea of conservation of mass, or that mass can neither be destroyed nor created. I'm sure you've heard that before. So we'll start with this idea of conservation of mass and see how in the ocean we can also think about that in terms of conservation of volume. All right, what is continuity? Well, continuity is when something is continuous. Okay, so what does it mean to assume that the ocean is continuous? Well, to quote Clinton Wynot, the professor who taught me this initially, what it means that the ocean is continuous is that there are no holes in the ocean. All right, there are no holes in the ocean, so that means the ocean is continuous. Good. Now let's see if we can understand why and quantify this a little bit. So we're going to start by thinking about conservation of mass in a closed box. So here is our imaginary box, and we're going to go take this and put it out in the middle of the ocean. It's an imaginary box, so it allows the water to come in and go out. And conservation of mass tells us that what goes in must come out. So that means that the mass going in must equal the mass coming out, or the rate of this mass flowing in must equal the rate of this mass flowing out. So we say the mass transport into the box must equal the mass transport out of the box. Okay, now we've talked about the fact that when we're looking at the ocean, when we think about mass, we can't just think about the mass of the ocean. We need to start by thinking about its density. So the density, of course, is the mass over the volume. So if the density is the mass over the volume, if we want to get the mass, we need to multiply by the volume. So that tells us that the mass is equal to the density times the volume. So using this quantity right here, that the mass is equal to the density times the volume, I can take this and plug this into the mass I have here and up here as well. And so I end up with rho in, V in, and rho out, V out. So now mass in equals mass out becomes rho in, V in equals rho out, V out. All right, so the next thing I want to think about is how I can relate rho out to rho in. So I can imagine that as something's coming into my box, it has some sort of density, initial density, and maybe that density gets changed slightly as it's moving through the box. And so in that case, I could say that my rho out is the same thing as my rho in plus some small change in density. So I will write rho out equals rho in plus some small change in density. Now I can take this value right here, rho in plus some small change in density, and plug it in to rho out right here in this equation. All right, so that equation now becomes rho in, V in equals the quantity rho in plus delta rho times V out. All right, so I'm starting to be able to simplify this a little bit. Now, the next thing we want to think about to make this even simpler, and a way that we frequently simplify things in the ocean, is looking at this very small change in density that we have right here. So this very small change in density is considered negligible. And we call this the Busanesque approximation. That tells us that changes in density in the ocean are negligible. And so we can, in fact, ignore that very small change in density. So now what we have is rho in, V in equals rho in, V out. So now I can just divide through by rho in. And if I divide through by rho in, that means that there is no longer rho in on either side of the equation, and all I'm left with is V in equals V out. So what I see is now I have V in equals V out. And the volume transport into the box must be equal to the volume transport out of the box. This is the conservation of volume now in a closed box. All right, so let's think a little bit more about what this means, this term volume transport. So I mentioned that it's kind of like a flow rate into our box. So the transport has to do with how much flux of this material is going through this area. So transport is the total flux through a given area times the area. And so what we end up with is something that's like a rate, because whatever thing we're talking about, with the transport of whatever thing we're talking about, it's going to be that quantity over time. That means that volume transport is volume per time. So it's, in terms of units, will be a meters cubed per second. That means that this flux that we have here is just our velocity. So the flux, when we're talking about volume transport, the flux is just the velocity of the water moving into our box. Using that idea, we can say that our volume transport in is going to be equal to our velocity times our area. Let's do a quick dimensional analysis to make sure that that makes sense. So we said that our volume transport is going to be meters cubed per second, and our velocity is going to be meters per second. Our area, of course, will be a meters squared. So that means that this side of the equation will also be meters cubed per second. So our dimensional analysis checks, and we can say that our volume transport is equal to our velocity times our area. So now our volume transport is equal to our volume in is equal to our velocity in times our area in. And our volume out is equal to our velocity out times our area out. And this gives us our conservation of volume in a closed box. This may seem pretty simple. And to quote Tally right here, this principle of continuity is so fundamental that it might not seem very interesting, but it is the one law that applies in all situations, regardless of how complex the system becomes. So if the principle of continuity is so important, we really need to find a good equation to help us apply the principle of continuity in all situations. So let's start by looking at a box that has sides dx, dy, and dz. So the volume of this box will just be dx, dy, dz. Now our conservation of volume tells us that our volume transport in is equal to our volume transport out. And we know from what we just looked at that that volume transport in will be equal to the velocity in times the area in, which in this case, we're going in the x direction. So that will be u in, a in, and our volume transport out will be u out, a out. Now, since we are saying that the velocity transport in, the volume transport in is equal to our volume transport out. So u in, a in equals u out, a out. All right, let's think a little bit about what is this a in. Well, we know that the area that we're going through, this area in, is just this box right here. It's just the side of this box right here. So the area is going to be the base of this square right here. So it's going to be this base right here times the height right here. And that will be equal on this side as well. So our area in and our area out, from the way we've drawn our box, we've made them equal, where they have the same base and the same height. And if we want to get this area, we see that that is just going to be this base, which is just dy, and the height, which is dz. Now, the next thing we want to think about is how our u out is related to our u in. So we can imagine that our water is coming in at some velocity, u in, to our box. And in this area, maybe that velocity gets changed slightly as it's going through our box. So there might be some change in our velocity as it's going through our box. So u out is going to be u in plus some small change in u. Using these values for a in and u out, we can rewrite our equation down here. So we can take this value for a in and for a out and put it in here for a in and for a out. And we can use this value right here for u out and put it in right here for u out. And so what we see is that u in times dy dz is equal to the quantity u in plus some small change in u, delta u, times dy dz. So now I want to go ahead and distribute this. So the first thing I want to do right here is distribute this u in and this du. So when I do that, I see that u in times dy dz plus delta u dy dz on this side of the equation. And on this side of the equation, I still have u in dy dz, which is great because now I notice that I have u in dy dz on both sides of the equation. And so I have u in dy dz on this side of the equation, and I have u in dy dz on this side of the equation. So I can just subtract u in dy dz from each side of the equation. And now what I'm left with is just simply du dy dz, and that, of course, will just be equal to 0. So du dy dz equals 0. Now, in order to think about how to quantify this, what I can do is divide by dx, so that will give me du dx, and multiply by dx. So I'm not doing anything fancy. I'm just basically dividing by dx, multiplying by dx. That's legal. I'm just basically multiplying by 1. So I get du dx times dx dy dz. And this quantity right here, of course, this quantity right here is just the volume of my box. Now, right here, I have du dx because I have been looking, we've only been looking at the volume transport in the x direction. So we've been doing the volume transport just in the x direction. But what we want is the total volume transport into our box and out of our box. And so the total volume transport through our box, we also need to take into account the y direction and the z direction. And so I can extrapolate the fact that in the x direction, I got du dx times dx dy dz. So in the y direction, I'm going to get dv dy times the volume of my box. And in the z direction, I'll get dw dz times the volume of my box. So now I can just add all these pieces together, and that will be my total volume transport through my box. So I have du dx plus dv dy plus dw dz times the volume of my box equals 0. So since this is all equal to 0, I can go ahead and divide through by that volume of my box, and I end up with just du dx plus dv dy plus dw dz equals 0. So my final equation is du dx plus dv dy plus dw dz equals 0. And this is the continuity equation. All right, so let's try to understand what this is telling us. This is saying the change in the u velocity in the x direction, plus the change in the v velocity in the y direction, plus the change in the w velocity in the z direction, that all those added together must equal 0. Well, the way that, again, I will give credit to the professor who taught me this, Clinton Wynot, used to always explain it, is we're thinking about this water parcel like chewing gum. So if we pull our chewing gum in one direction, if we speed up the velocity, how much water is flowing out of the box in one direction, then more water needs to flow into the box in another direction. And so if we stretch it out this way, it's got to get thinner this way. And if we squeeze it up in one way, it's got to get narrower on the other sides. So the example from your book shows this water parcel right here. And we see that the volume of this water parcel is conserved as it moves along. So it moves along here, and we can imagine that right here, maybe it's going over some bottom topography. And so the water gets pushed up into the box here. So dw dz, it's getting pushed up. So there's more water flowing into the box. It's getting pushed up here. And so it's got to stretch out somehow. And so it's going to stretch out here in the x direction. So more water needs to go faster out of the box this way. So du dx will change. Now, as we look at this picture here, now in this case, it's getting narrower in the x direction. So du dx has changed. And so in that case, it's got to stretch out in this direction. So dw dz must change. All right, I will post some problems for you to work on these ideas of continuity. And you can think about chewing gum. And go ahead and chew some gum if you want to. And I will talk to you soon.